So recombination, again, recombination occurs when the protons and the electrons come together and they create hydrogen atoms. We believe that happened when the universe cooled to the point of about 3,000 Kelvin. And so that's a redshift of about 1100. Okay, universe would have been about 380,000 years old. And you can calculate that with about 3,000 Kelvin temperature, the dominant wavelength would be really close to a micrometer, about 967 nanometers. So that's pretty short wavelength. That's going to be in the infrared. But as the universe has aged, that wavelength is going to become longer. So again, recombination, again, I think the term is really dumb because it wasn't any to it, it's just combination. But that's when the electron and protons come together to make hydrogen atoms. And so when that happens, then light starts shining through the universe. So if you look backwards and farther away, you look backwards in time, but you cannot see past that recombination point. You cannot see all the way back to the Big Bang. Okay. The reason is that light was, that the universe was opaque, so light could not pass. So all these events that happen in the first fraction of a second of the universe, or the first few seconds, nucleogenesis, in which they start making hydrogen and helium, that happens in the first 3 minutes of the universe, and then the background spectrum and all this sort of stuff, radiation, matter, energy combinations, all this stuff happened in the first a few 100,000 years, tens of thousands of years, 100,000 years or so. And so you can't see any of that because the universe was opaque at that point. And so you can only see back to that point 380,000 years after the Big Bang event. Okay. We call that the cosmic background radiation. And so this is basically the horizon as far as we can see. Zeldovich, Russian scientist, works out that over the years, as the universe is expanding, this cosmic background radiation will expand. So it's no longer a micrometer, it's going to be close to a millimeter. That makes it a microwave. And so something that's about a millimeter long, if you calculate that out, that comes to an effective temperature of about 3 Kelvin. And so the entire universe should be bathed in weak microwaves that peak about 1 millimeter. And so that's kind of what he predicted. Now, in the United States, Robert Dicke was also working on this and had read Zeldovich's paper and said, wow, okay, what we need is a microwave detector. And so, and then a big telescope, big radio telescope, specially made for microwaves. And so the problem was there was difficulty finding the sort of support for that. And so he started working with some engineers, electrical engineers, working at Bell Laboratories. Now, Bell Laboratories, communication stuff. So they were looking at an idea of using satellites to carry television signals. And so the idea would be, or not television signals, but phone signals. Eventually they became television signals. But the idea would be use microwaves, short wavelengths. And so they would have these big horns here, and the horn would have microwave transmitter that could like send signals out in space, and then the weak signals from here be bouncing around in here into the receiver. And so this was the idea of this big horn. Now the problem was testing out their microwave horn here, because they were working this. Dicke was working with them too, because he could use this eventually. He hoped to put on an actual dedicated radio telescope to search for the Big Bang. And so he was going to piggyback experiments on what Penzias and Wilson were doing. So what they did, though, was they discovered that wherever they pointed their horn, they got static. Well, they thought that because this thing is a big open container, that they had noticed that some pigeons had actually nested up inside of their big microwave horn. And so they thought maybe the pigeon droppings were the problem. And so they had graduate students going in there cleaning all the pigeon droppings. Well, they continued doing these experiments and they kept finding static. And they said, well, let's characterize the static. And they realized that if you characterize the static, that it was not the same at every frequency. In fact, if you made a graph of intensity versus the wavelength, you got something that was going to be, they didn't actually see all of that. They just saw part of the curve. They saw part of the curve, and they realized they could calculate where the peak should be, even though they couldn't detect the peak directly. And that peak was the right wavelength to correspond to black body radiation of about 3 Kelvin. That's exactly what Zeldovich predicted that we ought to be getting from the Big Bang. Okay, and so this was the first observational evidence behind the Big Bang. And this was a huge, huge discovery because up to that point, this was a big deal. The Big Bang was the leading model for the universe. So it goes all the way back to Vesto Slipher and his observations that you have things expanding, that rather you had the red-shifted extragalactic nebulae. Edwin Hubble, who comes along, and Hubble discovers this expansion of the universe along with Georges Lemaitre. So Hubble and Lemaitre both discover expansion of the universe. Lemaitre realizes exactly what it was. Friedman, of course, calculated the universe ought to be expanding. And all this, of course, was based on Albert Einstein and Einstein's observations. And so it was based on Einstein and his work and the field theories. And so, and then, of course, then you had Gamow and Bethe and Alford and all these other folks that were working really hard on this, came up with the initial idea of the Big Bang. They came up with the idea of the recombination. Zeldovich calculated exactly what the recombination ought to look like. And then Dickey came up with a way of measuring it. And then he solicited some engineers here to radio scientists to work with them in designing detectors. So the question, who gets the Nobel Prize? Is it the authors of the idea that the universe is expanding? That would be Lemaitre and Hubble, or Einstein himself for his work in general relativity that allowed this to happen, or Friedman, even, whose calculations from Einstein's work show this ought to happen, or Zeldovich, who calculated what it ought to look like. So who gets the Nobel Prize? It's Penzias and Wilson, who discovered it without knowing what they discovered. So they got the 1978 Nobel Prize in Physics for discovering the background radiation that solidified the idea of the Big Bang as the dominant model for the origin of the universe. And again, this is a later version of the Big Bang than what was originally postulated, but and this version too underwent some variation later. But that background radiation is measurable. And so in the late 1980s, NASA launched a spacecraft, part of the Explorer series. This is a Cosmic Background Explorer, to measure this cosmic background radiation. And so what we have here is a graph. The squares are the actual measurements, and the solid line is the calculated black body radiation for 2.725 Kelvin, just under 3 Kelvin. And you notice that it's dead on. We never, ever get this accurate that's that accurate. Now, it's got a slight anisotropy to it. In other words, it's not exactly 2.725 Kelvin in every direction. It's a little bit warmer than that in the direction of Leo, and a little bit cooler in the direction of Aquarius. And so your book has this graphic right here indicating it's warmer in Leo, cooler in Aquarius. Now, what's happening? Well, as Earth goes around the sun, we're moving this way and that way, and then the sun's going around the center of the galaxy. So all the motions in space cause us to be moving towards Leo and away from Aquarius. That means we are blue shifted towards Leo and red shifted towards Aquarius. Yes, we are blue shifted. So blue shifted means shorter wavelength towards Leo, red shifted, longer wavelength towards Aquarius. And so almost every cosmologist draws this diagram backwards, with the blue shifted as red for warm and the red shift as blue for cool. So I've never been a real fan of that, but that's how it's typically. So the cosmic background radiation, gas coming together, this is when the universe starts to become transparent. The gas forms. Eventually that gas forms into the very first stars. The stars have no metals at all in them, so we actually call them population 3 stars. And because they have to have so much extra mass to compensate for how warm they are, these are among the biggest stars that ever formed in the universe. Indications are they are vastly bigger than the stars that can form today. The biggest stars that can form today are a couple hundred solar masses. These were actually probably minimum a couple hundred solar masses to form. And then eventually they die, see the interstellar medium, we get more stars forming, this next group of stars, they clump together to make star clusters and galaxies and so forth, and then we have the universe as we see it today.